So our next topic of discussion, that is the Ampere's law application, is the solenoid, right? Solenoid. Solenoid. What is the solenoid? Suppose there is a plastic cylinder like this, right? And number of turns, copper wire turns are wound over this, right? Like this. This is the copper turn, right? Like this. And although this is the infinite long, if you give the current, if this current flows I, so the current flows in every wire is I. Is it clear or not? And this is, initially we will consider the infinite length, right? Infinite solenoid. So you may consider like this, right? Infinite length. Are you getting or not? This is the infinite length current carrying wire. All right. The property of the solenoid is small n, right? What is small n? It is the number of turns per unit length, right? Number of turns per unit length. Is it clear or not? So listen one thing. If you consider only the one coil, right? So the magnetic field due to one coil is what? Like this, right? The magnetic field due to one coil on the axis is B is equal to what? Mu naught I upon 2R. Mu naught I upon 2R. Is it clear or not? So when number of turns are wound on this plastic cylinder side by side, so the magnetic field is produced inside the solenoid. Are you getting or not? So the magnetic field is produced like this. This magnetic field is inside the solenoid, and the outside the solenoid no magnetic field exists. If you consider this is the turn, so the magnetic field here is like this, right? Like this, right? But if you take the number of turns, right? So the magnetic field become straight line, in straight along the axis of the solenoid. Are you getting or not? So we have to find the magnetic field inside the solenoid. Are you getting or not? Right. This magnetic field inside the solenoid comes to be mu naught n into I. Right. You have to remember this. And the I is what? I is the current in each turn. Suppose the current in the wire is flowing I, right? Where n is the number of turns per unit length. And how does it come? It can be proved with the help of the Ampere's law. Is it clear or not? Yes. To prove that the magnetic field inside the axis of the solenoid mu naught n I, we will take the help of the Ampere's law. To apply the Ampere's law, we have to choose an Amperian loop. Here, we will take the Amperian loop like this rectangle. This is A, B, C, D, right? This is the Amperian loop. Are you getting or not? Yes. Now, this is the side view. If you make the cross section view, right, like this. So, suppose this is the cross section view. We are taking the length of this solenoid, length of this Amperian loop is what? Small n. Are you getting? You will see that here the current is going inside, like this. Current is going inside. The current is going inside, and here the current is coming from out, like this. Is it clear or not? Yes. This, the current coming out, it is current in. The current is coming like this and going, like this and going into the board. Coming out of the board, like this and going into the board. Going into the board, coming like this, right? It is coming like this. It is into the board, then it comes out from the board. It is going into the board, it is coming out of the board. You understand this thing or not, you tell? Right. So if you consider the L length, right, this is the L length, this is the Amperian loop, suppose A, B, C, D. So this is the current, all right. This is I. Many number of turns are I. right? You tell me. So if the length is L and the number of turns per unit length, for example 100 turns per meter, right? It means if n is the number of turns per unit length, it means in 1 meter, how many number of turns? N. Suppose the n value is given as 500 turns per meter. What does it mean? In 1 meter, how many turns? 500. If n turns per unit meter are there, so it means in 1 meter how many turns? Say n. So this is the length L. So how many turns? The total length is L. 1, 2, 3, 4, 5. So how many turns are there? No. In 1 meter, it is n. In 2 meter, it is 2n. It is 3 meter, it is 3n. 500 tons in per meter. It means in 1 meter, in 2 meter, 2 into 500, right? So in L meter, L into 500. So if in 1 meter n turns, in L meter n into L. So these are the total number of turns. 1, 2, 3, total number of turns. So therefore what is the current enclosed? I enclosed. I plus total number of turns are capital M. So in 1 turn the current is I. These are the total number of turns and L into I. Is it clear or not, you tell? Right. Copy this first a little bit. I enclosed में लिखा है, I enclosed number of turns कितने हैं? 1, 2, 3, 4 n. So I enclosed में लिखा है number of turns, right? Small n into I. Right. So this is the current enclosed. All right. So now we can apply Ampere's law. Now apply Ampere's law. Ampere's law, right? Ampere's law. What is the Ampere's law? If this is the Amperian loop, this is suppose the orientation of the Ampere's loop, right? So integration of B dot dl is equal to mu naught into I enclosed. And what is the I enclosed? You tell. The I enclosed is, yes, n into L into I. Is it clear or not? Yes. So this is the B dot dl along this loop A, B, C, D, right? So now see A, B, C, D. Now you can divide this integration by parts, in parts. Integration B dot dl from A to B, right? A to B plus B to C, B dot dl. Then C to D, B dot dl. Then again D to A, right? B dot dl is equal to the mu naught into I enclosed is nothing but mu naught n L I. Is it fine? Look, if you want to integrate B dot dl along the line or along the path AB, you will consider the small length dl. Are you getting or not? Small length dl, right? And inside there is no magnetic field outside the solenoid. Only the magnetic field is present inside the solenoid. Is it clear or not, you tell? Right. Outside it is 0. Fine. And here, if you consider this is the magnetic field vector and this is the dl vector. So what is the angle inside? Say 90 degree. B is this and dl is this. So here the angle is what? Say 90 degree. This angle is 90 degree. So B dot dl is what? 0. B dot dl is 0 inside and outside no magnetic field. So from A to B, if you integrate B dot dl, what the answer you will get? Say 0. In the same way, outside, if you are integrating, what is the magnetic field outside? It's 0. So therefore, if it is 0, then it is 0. Here the angle you can assume to be 90 degree. All right. In the same way, when you integrate along C to D, from C to D, the dl vector is, this is the dl vector. Outside the magnetic field 0 and inside, although the magnetic field is present, but what is the angle? 90 degree. So here the angle you may assume to be 90 degree and therefore it become also 0. Right? So only the value of the B dot dl we can get from D to A. If you consider this is the element dl vector and the magnetic field also present in the same direction. So here, if this is the dl vector, the magnetic field is also in this direction. What is the value of theta here? 0. So here the theta is what? 0. If theta is 0, then B dl cos 0, right? Cos 0 is 1. So the B dl from D to A is equal to mu naught NLI. Are you getting or not? Yes. B comes out from the integration because it is constant, right? Mu naught NLI. Is it fine? Yes. From D to A, from D to A, it is the small element dl. So yes. Integration of dl mean you have to take the length, this length. And what is this length? Say it is L. So its integration from D to A comes to be B into L and mu naught NLI. LL will cancel out. B is equal to what? Say mu naught NI. So this is the magnetic field inside the long solenoid. Inside long magnetic induction. Magnetic induction inside long solenoid. Right? Copy this. So now see, we see the magnetic field inside the solenoid, right? B inside finite length solenoid, finite length solenoid, right? Finite length solenoid mean this is the solenoid, right? And its length is finite from here to here. This is the axis, all right? Again, its property is small n. Small n is number of turns per unit length. Is it clear or not, you tell? So here this point is A, this point is B. Start from here. The current is going, right? Current carrying coil is wound over this solenoid. Suppose this is the point P where you want to write the magnetic field. The end A, right? Make angle theta 1 like this. The end B, make angle theta 2 like this. Is it clear or not? So here the magnetic field B, right, is written as, right, mu naught Ni by 2, right, cos theta 1 plus cos theta 2, you will remember. Is it clear or not? Theta 1 is the angle made like this. Theta 2, the angle made by this line with the axis like this. For example, I'm giving you example, right? For example, if number of turns per unit length is 100, right? Turns per unit meter. Current I is supposed 2 ampere, right? This is the solenoid. This is the point where you have to find the magnetic field. Suppose this is the 37 degree and this is 53 degree. Are you getting or not? This angle is 37. This angle is 53. Is it clear or not? So at this point you have to find the magnetic field mu naught Ni by 2, right? What is the cos theta? Yes, and what is the cos theta 2? 53. So I'm putting the value, mu naught value is 4 pi, right? I'm writing this side. B is equal to 4 pi into 10 ki power minus 7 upon 2. What is small n? It is 100. What is I? It is 2 cos theta 1 37. Fine. Plus cos 53. Is it clear or not? So 2 will cancel out, 4 pi into 10 to the power minus 5 it is. Cos 37, right? It is 37. It is 4 upon 5. It is 3 upon 5, right? So it is 7 upon 5, right? And multiply by 4 pi into 10 to the power minus 5, right? So it is 28 pi by 5 into 10 to the power minus 5 Tesla. Is it clear or not, you tell? Copy this. So listen one thing. Although there is a derivation for this formula, but it is not useful for you, right? So that is why you have to remember this formula in the same way, right? Right. Special cases. What are the special cases? For infinite solenoid. Infinite solenoid. Tell me. For the infinite solenoid, the point A, suppose, is reached to be infinite. Listen, if this point A, if you increase the length, so what is this angle, you tell? Initially, this angle is theta 1, right? Now, if this point A reaches that point, so the angle is reduced. Yes. And if it is infinite, this angle is reducing to 0. In the same way, suppose the length a little bit increase. So this point B make this angle. So the angle is reduced, then reduced, then reducing. And if it is going to infinity, then angle theta 2 become 0. So for infinite solenoid, theta 1 and theta 2 become 0. Right. So in this formula, B is equal to what? Mu naught Ni by 2, right? Cos 0 plus cos 0. 1 plus 1, 2, and it is cancel out. It is equal to what? Mu naught Ni. So this is the same thing or same magnetic field we have found using the Ampere's law. Is it clear or not? Yes, sir. Right. Copy this. So this is the magnetic field inside the infinite solenoid. What about the semi-finite? After that you can write here semi-infinite, or on one end of long solenoid, right? On one end of long solenoid. One end of long solenoid mean the solenoid start from here, right? From B point is this, and it is infinity, right? The current is this. So at this point you have to find. So the point A tending to 0, this angle theta 1, the A point is tending to infinity, so theta 1 tending to 0, right? And if this angle, this point B coming near to the point, right? So if the point is over here, this is the angle. If point B comes over here, the angle become 90 degree, right? So this is the theta 2, right? This is what? Theta 2, it is 90 degree. And for this, the angle theta 1 is what? 0, and the theta 2 become 90 degree. Is it clear or not, you tell? Yes. So what is the magnetic field at this point? B. Mu naught Ni by 2 cos 0 plus cos 90. Cos 90 is 0, cos 0 is 1. So the answer is mu naught Ni by 2 is the correct answer, right? Copy this first. So read this question. The length of the solenoid is 0.1 meter, right? This is the length, suppose. And its diameter is very small. Diameter is very small, mean it is very small, and the length is this. Are you getting or not? It is very small, mean 1 millimeter like that, right? So you can treat this is the solenoid very lengthy, right? That is, we can apply the formula for infinite solenoid here, right? Suppose this is the length, so I am making this like this. This is the length 0.1 meter. A wire is wound over in 2 layers. The number of turns in the inner layer is 50 and outer layer is 40. Suppose this is the inner layer, right? So number of turns is what? Say 50. And the outer layer is what? Say 40. And the strength of the current flowing in 2 layers in opposite direction. It means if in the inner layer the number of turns are 50, the current is flowing in this way. Fine. And the outer layer, the current is flowing in opposite direction. Is it clear or not?
Yes.
Like this. And the number of turns are what? Say 40. Right. So if one layer produces the magnetic field in one direction, the other layer, outer layer, produce the magnetic field in other direction. Is it clear or not?
Yes.
So what is the magnetic field inside is equal to mu naught Ni, right? So the net magnetic field, you may write B1 minus B2. Mu naught, although the current is same, the current is what? Same. Mu naught N1I minus mu naught, say N2I. So it is mu naught I N1 minus N2. Mu naught I, what is N1? N1 is small n is number of turns per unit length. You will remember this. So it is 50 divided by length. What is N2? What is this? Is N1. What is N2? 40 upon per unit length. Is it clear or not, you tell? Right. So if you put the value, it is 4 pi into 10 to the power minus 7. The current I is 3 ampere. When you simplify it, is 500 minus 400. It is 12 pi into 10 to the power minus 7 into 100. 12 pi into 10 to the power minus 5 T4 Tesla is the net magnetic field. Is it clear or not, you tell? Copy this. So in this illustration, read this question. A closely wound solenoid 80 centimeter long have 5 layers. Right, this is the solenoid and the 5 layers mean 1, right, 2, 3, 4, 5, and the number of turns are 400 in each layer, right. The length is 0.8 meter, you may write. The diameter is 1.8 centimeter and it is of not used, right, because the magnetic field inside is what? Say mu naught Ni. Is it clear or not, you tell? Listen, due to the 5 layer, you have to multiply by 5. Is it clear or not? So 5 into mu naught, what is the small value of n? N value, small n is n upon L. 400 upon 0.8. Is it clear or not? So this is 4000 upon 8 is equal to 500 tons. The small n value is what? 500. And what is the current I? Is 8 ampere. Are you getting or not?
Yes.
So this is the magnetic field in the part A. Inside the solenoid, they are asking. This is the magnetic field inside the solenoid is mu naught Ni multiplied by 5 because there are 5 layers. So 5 into 4 pi into 10 to the power minus 7. This is 8 पंजे 40, 400, right. 80 pi into 10 to the power minus 4. 80 pi 8, and this is equal to 8 pi into 10 to the power minus 3 T4 Tesla is the correct answer, right. So this is the magnetic field inside the solenoid. Fine. And what about the on the x on the end position here, B dash? Tell me. On end, the magnetic field is just half of this, if you understand. Is it clear or not? So this is the magnetic field inside, and just take the half of this, right, because mu naught Ni by 2 on the end point, right. So 5 mu naught Ni by 2 you may write, but we have calculated earlier. So the answer will be 4 pi into 10 to the power minus 3 Tesla. This is on one end. Fine. Copy this. The length is big and the diameter is very small. So you may consider this is the infinite only. Right? If this is the up to this, right? It is very, very small, but it is 0.8 meter, suppose. So although this is the what is the difference between finite and infinite? Infinite does not mean from here to America. Are you getting or not? The long wire you can see in the field the current carrying wire, they are long, so long, right? So you may treat it as the infinite. Are you getting or not?
Yes.
Right. So if you, what is the infinite mean? If you consider this the point and this angle is approximately be 0.
Yes.
Are you getting or not? So for 0.18 meter and this is 1.8 centimeter. So this diameter is very small as compared to the length. So angle made on the point on the axis by this end will be approximately 0 like this. Right? You can see. If it is 0.8 meter and it is 0.4 meter,
Yes.
right, then it cannot be the infinite, right, because the angle will be very greater than 0, right?
Yes.
So read this question. This is straight long solenoid produce magnetic field at the center, right? Suppose this is the solenoid and the magnetic field at the center is B. Fine, it cut into two equal parts. Okay, now the same number of turns are wound over one part in double layer. So in this case the magnetic field is mu naught Ni, suppose, and the small n is capital N upon L. Is it clear or not?
Yes.
Now the number of turns are what? Say n into L. Is it clear or not?
Yes.
So if its length become L by 2, right? So now the same number of turns, how many turns? Say N L by 2. So it is wound over the L by 2 length, right? So what is the number of turns? Say NL. So in this case the total number of turns is NL
Yes.
and the length of the solenoid is L by 2.
Yes.
So what is the N dash for this? Total number of turns per unit length. So what is the capital N? So capital N is N into L upon L by 2. So it is equal to 2N. So for this the N dash become 2 times of N. And what is the B dash at the center? The B dash at the center is nothing but mu naught N dash I. So mu naught, what is N dash? N dash is 2N into I. It is 2 into mu naught Ni. The mu naught Ni is nothing but what? B. It is given in the question. So the magnetic field become 2 times here. Are you getting? Should I explain once again?
No, sir.
Right, copy this. So read this question. In this question, the given figure is like this. This is the solenoid and the point B, you have to find the magnetic field such that this angle is 30 degree and this angle is what? Say 60 degree. All right. So what is the B? Say mu naught Ni upon 2 cos theta 1 plus cos theta 2. Right. So this is mu naught Ni by 2 and this is root 3 by 2 plus 1 by 2. So the answer is mu naught Ni or root 3 plus 1 by 4 is the B. Is it clear or not, you tell?
Yes.
Copy this. So the next topic is toroid. Toroid. Right. What is the toroid? Toroid is the same toroid. Right. If this, it was the solenoid, right? It was the solenoid. So if you turn this solenoid into the circular arc like this is the, it become toroid. So number of turns are wound over the circular cross section like this. Is it clear or not, you tell?
Yes.
Right. This is the magnetic field like this. You can think, right? This is the current. Fine. Right. And this is the current. It is coming like this. Fine.
Yes.
It is, this current is coming and this current is going in this way. Are you getting or not? Like this. Right. So look at the figure. Right. This is the current. The current is, this is the current, right? The current is coming like this and it is going in this way. Is it clear or not, you tell?
Yes.
So here the number of turns are given. Instead of number of turns per unit length, the total number of turns, this is the total number of turns, and the current carrying is I. You understand or not, you tell?
Yes.
If you suppose the inner radius is A, outer radius is B, although the A and B are very very close to each other, right? If you want to find the magnetic field inside, right, inside it, so the magnetic field will be like this, right? The magnetic field is produced in this solenoid inside. These are the circular magnetic field are produced. Is it clear or not, you tell?
Yes.
To find the magnetic field, what you have to do, you have to take the Gaussian, to take the Amperian loop. Suppose this is the current going into the plane like this, and this is the current coming out from the plane. Fine. So if you make the cross section, this is the inner and outer radius, right, like this. So the current is going here like this into the board. Current is coming, right, and going into the board. Current is coming 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 and going into the board. All right.
Yes.
Like this, like this, like this, like this. Is it clear or not, you tell? So the magnetic field inside the solenoid are circular. You take the radius r. Suppose the r is the average radius a plus b by 2, right? A and b are approximately same. If the a and b are not given, the radius r will be given of the solenoid. You can take the small r. So you have to take an Amperian loop like this. The magnet, if this is the dl vector and this is the magnetic field vector b, is it fine or not?
Yes.
And this is the magnetic field vector. So what is the angle between dl vector and b vector? It is 0. If one loop, the current is I. So in one turn, how much current is? Say I. And how many turns are there? I. Total number of turns are N. So what is the current enclosed in this Amperian loop? Ni, right? So here we go. The Ampere's law, B dot dl is equal to what? Mu naught into I enclosed. What is the current enclosed in this Amperian loop? Say capital N into I. The property of the toroid is capital N, and the small n is the property of the solenoid. And here the theta is 0, B dot dl is equal to mu naught Ni. And what is the integration of dot dl? In dl, it is total circumference. The summation of all dl is equal to 2 pi r mu naught Ni. So what is the B? Mu naught Ni upon 2 pi r. Is it clear or not, you tell?
Yes.
So this is the magnetic field inside the toroid, having the total number of turns is n, while in the solenoid it is small n, the total number of turns per unit length. This is difference, right? Copy this. So read this question. There is a toroid and non-ferromagnetic core is there. The inner radius is given and the outer radius is given. It is inner radius and it outer radius, right? So A is what? 25 centimeter. B is what? 26 centimeter, right? So what is the mean radius? R is equal to A plus B by 2. 25 plus 26 by 2 is equal to 25 by 5 centimeter. Is it clear or not, you tell?
Yes.
Right. So I will take the mean radius. This is the mean radius. Listen one thing. When the number of turns are like this, so the magnetic field is produced only inside the toroid. Here the magnetic field and here the magnetic field is 0. You understand or not? So B is equal to what? Say mu naught Ni upon 2 pi r. Is it clear?
Yes.
So it is inside. The part A. What is the part A? Outside the toroid. Tell me. Outside the toroid, the magnetic field is. And what is the part B? The inside the core of the toroid. It is mu naught. Mu naught value is 4 pi into 10 to the power minus 7. What is the total number of turns? Say 3500. What is the current I? I is the 11 ampere. It is 2 pi into R. What is the mean radius? 25.5 into 10 to the power minus 2. Is it clear or not, you tell?
Yes.
Right. So when you will calculate approximately 3 into 10 to the power minus 2 Tesla, you will get the magnetic field inside the toroid. Is it clear?
Yes.
Also, what is the third part? In the third part, in empty space surrounded by the toroid. If this is the toroid, this is the empty space. So in this empty space, the magnetic field is also 0. Right? Copy this.